out is no longer blue, and now anybody listening at home starting at 1:40 is going to be able to hear us. Okay? All right, so here we go. Any last questions? Any teachers have any issues? All right, perfect.
There's a couple people that might be coming in.
That's absolutely fine. Yeah, that sounds good. In fact, we might leave the doors open possibly. Hey, Lyle, are you still there?
We sure are.
All right, we are completely ready to go here.
Okay.
Things are looking good. About 100. Vehicle reports entry interface. So I'm beginning to feel the atmosphere as we go in here. It is reporting that we are seeing G's on the order of 11 to 12 hertz G's. Commercial 2 is starting. We are now getting telemetry from altitude. We should have pressure deploy around Mach 1.7. Parachute is deployed. We are decelerating. Features have separated, we're down to ground. We're down to 90 meters per second at an altitude of 6.5 kilometers per second. Standing by for batch separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky green. Sky green is starting.
Eagle Dodge, you remain strong.
Touchdown confirmed. We're safe on board.
Got thumbnails.
Well, hello and welcome. My name is Lyle Tavernier. I'm speaking with you live from NASA's Jet Propulsion Laboratory in Pasadena, California. And joining me today is our special guest, Todd Barber.
Hi, everybody. How you doing?
Todd is a propulsion engineer here at the Jet Propulsion Laboratory. He works on the Cassini mission and has a lot of experience with Mars missions as well. You've worked on a couple different Mars missions, correct?
That's right, Lyle. And good afternoon, Syracuse. Orange Man, right?
Oh,
Is that
yeah.
your local? Yeah.
Yeah, definitely.
Cool. Well, I always like the Syracuse. I always root for you guys. And you're Big East, is that right?
Yeah, right at the end of being in the Big East. We're moving to the ACC next year, so.
Oh, really? Okay. Well, good luck in the ACC. Happy New Year, everyone. And we're coming to you live from Pasadena, California. So it's 3 hours earlier out here. Windy day. We have our Santa Ana winds kicking up. And what's it, about 60 degrees or so?
Yeah.
And we hope you're enjoying the 2013 so far. I guess the Mayans were wrong. We're all here, so that's good. As Lyle said, I've worked on a lot of Mars rovers over the years. I didn't get to work the first one. We had this cute little rover called Pathfinder, which was our first Mars rover, about the size of a child's wagon or a microwave oven. That was back in the mid-1990s, and that worked really well. I think Lyle's even maybe going to pull up the next rover that I did work on. That's my shirt right here. I should have worn my MSL shirt, the Curiosity rover, but I did get to work on the intermediate rovers. These are the twins. We love the twins, Spirit and Opportunity. They launched in summer of 2003. I nearly missed the launch of one of those at peril to my own career because I had to come to your fine state summer of 2003. My church choir got invited to sing in Carnegie Hall. So they said, launch is going to happen. I said, well, you know, launches come 4 or 5 times a career. Carnegie Hall is once in a lifetime, so I got to go sing with my church choir. Luckily, the launch was delayed, and I didn't miss anything. So I got back for the launches in summer of 2003, and we sent those on the way to the Red Planet. They landed January of 2004, Spirit on the 3rd, and Opportunity on the 24th, for a 90 Martian day mission. A Martian day is called a SOL, S-O-L. Martian day is a little longer than an Earth day. It's 24 hours, 39 minutes. So that means if you're working on a Mars rover, especially early in the mission, you have to go on Mars time. So you come into work 39 minutes later every day. And sounds great, get a little extra sleep, but as you might imagine, after a while, it's pretty tough to come in the middle of the night, and what if your family's still on Earth time and stuff like that? It gets difficult. So those missions were supposed to last, Spirit and Opportunity, for 90 Mars days, about 92 Earth days, and one of them bought the farm about 6 years and a few months into its 90-day mission, and that was Spirit. So imagine that way outlived its lifetime. And then there's Opportunity, it's still going, and in fact on the 24th of this month we celebrate 9 years into its 3-month mission. So we really built that thing really excellently well. And of course it's still astounded us that it's working and doing science on the Red Planet. Not content with those rovers, which are about the size of golf carts or so, we wanted to send a new big bad rover to Mars, and that's what we did with Curiosity, Mars Science Laboratory. We launched 2 days after Thanksgiving in 2011. Here we are, big rover for big science, and this rover, it weighs a ton on Earth. Mars gravity is only 3/8 of Earth, so it weighs about 750 pounds on Mars. And it's bigger than a Humvee vehicle, huge 6-wheel drive rover, scientific capable robot to do our wonderful exploration for us. And I understand you've already seen the 7 Minutes of Terror video, is that true, about how we landed?
Yep.
So that's the craziest landing scheme with the heat shield and the parachute. No airbags, it was too big for airbags, so we had to use this crazy sky crane system. It all worked perfectly last August, as maybe some of you saw on your summer break, if you stayed up really late. I think it was 1:30 in the morning Eastern time when we landed. And one of the best nights of my life for sure, Lyle.
It was a lot of fun, I remember.
So great. All that hard work. Some people work 10 years of their life for that moment. And I'm happy to say everything worked perfectly. We've been driving the rover ever since. That was my last night on the project. I'm a propulsion engineer, rockets. So basically I helped get it from Earth to Mars, 352 million miles. And 8.5-month journey, so even when we had a bad day, I said we traveled 1 million miles that day, so like 2 round trips to the moon. It's not too shabby. And of course then the propulsive descent as part of the 7 Minutes of Terror. I had very little to do with that, but just enough to celebrate and get excited when it worked. And then that night was my last night on the project, because we don't need rockets on the surface. We have electrical motors to drive the rover. You don't want a rocket-powered rover. It would fly over cliffs or crash into mountains and things like that. So we've turned it over to the surface team. They're finding amazing things, driving, exploring. They went on Mars time for a while. It's been a heck of an adventure so far. We hope the mission lasts for 1 Martian year, which is about 2 Earth years, 23 months. And given Spirit and Opportunity's performance, we expect this rover will last many years too. And we're just very, very excited. We landed in what was likely an ancient lake bed, a really low place on Mars called Gale Crater. And Lyle may be pulling up a photo of that now. We were able to get the uncertainty in landing really small down to where we could land in this very scientifically juicy location, give the scientists what they wanted. We've already found really strong evidence that there was a flowing stream of water there, and we're not even up to the mountain yet. There's a mountain in the middle of this crater called Mount Sharp, 16,000 feet high, and let's see, there's an alluvial fan there, which is like the Mississippi River Delta, so a river spills out and all these sedimentary rocks are probably there. We landed at a very, very interesting spot. The black ellipse shape, you'll learn about ellipses in high school geometry and algebra. That was our uncertainty on landing. And blue means low. There's no water there today, but we think there was water there billions of years ago. And so we're going to explore that for a while, and then in February start driving to Mount Sharp. And this is a 16,000-foot mountain. As you can see, it's a big mountain. It's bigger than any mountain in the 48 states. Not quite as high as McKinley, but definitely smaller than Everest. But for Mars, it's a huge, huge feature. And as layered bedrock, kind of like our Grand Canyon. So that's why we want to go there. We want to understand the layers and see what the rocks have to tell us. So I probably talked more than I wanted to as an introduction there. I tend to do that. Any questions so far about 7 minutes of terror, what it was like to fly this beast to Mars, how you can get a fun job like this, working for NASA, doing space exploration, anything like that? I understand you're in middle school, so this is a very critical time in your careers. You're going to start choosing paths. You'll have some choice in your classes. You can choose the easy math and science path or the harder math and science path. And sometimes it's hard to force yourself to take that hard path, but that is the key for these kind of fun jobs where I get to come to work every day and feel like I'm really coming to play. But don't tell my bosses. But this is a place I'd come work for free. If I didn't have to pay bills, I'd still come here. So, any questions so far?
Yeah, these guys have a whole bunch of questions. We just wrapped our chapter on gravity, so we talked a lot about escape velocity, orbital velocity. We looked at the launch of the Mars rover, but didn't talk a lot about how the trajectory works for getting there, and didn't talk tons about how you land. And we're really interested in a lot of those speeds and how exactly you make those calibrations along the way. At least I am. We also come front-loaded with a whole bunch of questions coming from kids, and if you don't mind, I'm just going to have them rifle them at you, and you feel free to take it in whatever direction you want to go.
That sounds excellent. And maybe to address your first question first, do you have the home and transfer? It's in my slides, if nothing else, down there at some point. I'll start talking to this while we look for the slide. That's wonderful you're learning about escape velocity and gravity. Gravity is, I mean, as we know, trying to get out of bed early in the morning, it's hard to get out of bed, and that's one manifestation of gravity. But it's really hard to get off the Earth. That's a huge gravity well. That's why we need this enormous launch vehicle, the Atlas V, to get us enough energy to attain escape velocity. Now, we have escape velocity from the Earth, of course, which we need to get to Mars, but not escape velocity from the solar system. Some of our missions actually have solar system escape velocity, like the Voyagers and the Pioneers, so they'll never see the sun again. That takes even more energy to get out of the sun's gravitational grip. What we do, we're going to pull up a slide now. This is a top view of the solar system looking down, and the sun is in the middle. Lyle's pointing to it there. And then the Earth has a nearly circular orbit around the sun. He can go around that circle there. A little hard to see on the screen. Maybe I can see it well. Hopefully you can see it well where you are too. And Mars is in a nearly circular orbit, but it's more elliptical, more egg-shaped, and he's outlining that now. And what you end up doing, there's many ways to get to Mars, but they cost a lot of propellant. We want to get as much science there as possible, and with as little propellant as possible for a given launch vehicle. So we do what's called a home and transfer orbit, and it's half of an ellipse. An ellipse is in this egg-shaped orbit. So where it's blue there is our launch period. We launched on the second day of our launch period, and Lyle can trace out what our path was out to Mars. This is the 352 million miles. Now, of course, any football fans there, you know, you don't throw to where the receiver is, you throw to where the receiver will be. And that's what we had to do in that home and transfer. So Mars at launch was up at the about 11 o'clock position. It goes slower around the Earth, around the sun than the Earth does because of good old Kepler's laws of motion. And we met up with Mars in August 5th of last year. And those TCMs, or trajectory correction maneuvers, it's like a par 6 golf shot. We got an eagle. We only needed 4 of those 6 maneuvers. And that was my main job on the mission, is firing those rockets, keeping it on course, and getting it to the right entry location. I can't remember what our launch speed was. It's higher than later speeds, although we're going down about 8,000 or 9,000 miles an hour by the time we're out towards Mars. But then Mars gravity itself, even though it's only 3/8 of Earth's gravity, starts accelerating us and sucking us in even faster. So by the time we hit the Mars atmosphere, we're going 13,000 miles an hour. And that's a problem. That's way too fast to land. We've got to start shedding zeros, and that's what 7 minutes of terror is all about. The heat shield knocks a zero off. We're down to about 1,000, 1,300 miles an hour. We do a supersonic parachute then on nearly Mach 2. But even on Mars, since the atmosphere is so thin, that only gets us down to about 200 miles an hour. maybe 150. So on Earth, we jump out of airplanes, and without a parachute, we go about 120 to 180 miles an hour, depending on if you're spread eagle or nose diving. On Mars, even with a parachute, that's all the slower we can get, because the atmosphere is so thin. So we needed more. That's where the rockets and the sky crane and the real soft landing at a few miles an hour, that's what allowed us to be safe when we touched down on the red surface, the planet's red planet surface. So that's kind of the orbital mechanics. Those Earth and Mars obviously have to align together before we can send the rover. And unfortunately, that only happens every 26 months, every 2 years and 2 months. So we actually were hoping to launch September of 2009. We had a number of technical issues on the rover, and we just weren't quite ready. Maybe we were a couple months behind, but the problem is Mars makes you wait. So even if we were ready to go in November of 2009, the planets weren't ready again until November of 2011, 2 years, 2 months later. So that was a hard time on the project when we couldn't meet our original launch date. But, you know, I think if we'd have tried to launch then, we probably would have failed. That's my personal opinion, maybe not NASA's. I don't think we were ready. So I'm glad we waited and to get the glorious success that we had last August. So did that cover the orbital mechanics part of the mission fairly well?
Oh yeah, that might have been my question in disguise. I might have passed it off as the kids. But here comes some of the kid stuff now. Dave Neff, I'm going to start with you, if that's okay, nice and loud so people can hear you.
Are there any flaws to the most recent rover? If there are,
That's a good question. Yeah, that's a good question. You know, since landing, the only thing I've heard about is the weather sensor, which measures pressure, temperature, wind speed, and there's redundant, and we're going to show a picture of it. It's these little growths on the neck of the rover, and they're rims. I forgot what it stands for. I apologize. It's all acronyms.
The ROVER Environmental Monitoring System.
Wonderful. We have our acronym expert next to me. Thank you so much. My whole life is acronyms. JPL, NASA. I went to MIT. It's just, you know, it's acronyms, acronyms, acronyms. Those little sensors are working great, although we think during landing the rocks and dust kicked up. Maybe a pebble hit one of the wires and disabled some of our ability on one of the sensors to monitor the weather on Mars. But there's redundancy, so really no loss. And that's, you know, given all the things that could have gone wrong during the 7 minutes of terror, if that's the only problem we've had on the mission so far, that's really unbelievable. But thanks, that's a good question. And there's a press release about that too, about the loss of that weather sensor. We'll probably make a design change so it doesn't happen again, but again, luckily, we believe in redundancy. It saved our bacon this time. Good question, though.
Ms. Peterson, question?
Did you have more than one job while working on the Mars rover?
I think I heard that. Did I have more than one job while I was working on the rover?
Yes.
Yeah, and that's a great question. The answer is absolutely yes. I've been on Cassini mission to Saturn, which is a Saturn orbiter, and I'm the head propulsion guy, so I fire the rockets, keep it on course around Saturn, and fly by the moons and all these things. And Saturn was very patient. Cassini was very patient with me. We're going to pull up, can I show the occultation image? I want to show this picture, just to give Cassini a little love too, although I love the rover. Look at this picture that we took a few years ago. This is a real picture of Saturn. We had one time during the mission, we've actually had one more since then, but back then we had one time during the mission where the sun was behind Saturn as seen from the spacecraft. So we took this gorgeous many-hour exposure, and of course Saturn is lit up from behind, the sun coming from behind the disk of Saturn. And not only can you see Saturn itself in this backlight, you can see the main rings and details in the rings. You can see the faint, I believe it's the G ring that is put out by one of Saturn's moons, Enceladus, an icy moon that spews ice crystals into space with ice volcanoes. Should be geologically dead, but it's not. And we discovered a new ring with this image. And as great as all that is, it's not even the best part. About at the 10 o'clock position, it's pretty hard to see. Do you think we can...
On this one, I can't point to it, but
okay.
If you keep describing it, I might have a slideshow that will actually highlight it for us.
At about the 10 o'clock position, there's this little tiny dot that is outside of the bright rings, but inside that blue fuzzy ring. I think it's outside of that thin ring that's outside the brightest rings. That's called the F ring, kinky braided ring. There's this tiny dot. Any guesses on your end? Can you see the dot, first of all?
Yeah, I'm up
It's
for
about-
this one. I'm looking. Anybody have it? I don't know.
Yeah.
Maybe I'm getting close.
I'm gonna switch to a different image.
Yeah.
Okay, oh, we got it. Lyle, save the day. We have an image coming up, and we're going to circle where the dot is. Okay.
That was what you were looking at then, so we saw it.
Okay, from the audience, any guesses what that dot is?
Just talking.
A moon?
There is a moon in that picture, and that's a great guess. There's something else in that picture, too. But you can only see one. It's two bodies that are next to each other, but they're far away, so you can't... I'll give you a hint. You're looking back towards the sun from Saturn. What do you think that might be?
Another planet?
Yeah, you're getting warm. It's another planet. Which one?
Dwarf planet?
Wait,
So, I'm sorry, what was that?
You don't like the big blob of everyone answering at the same time? Anybody want to raise their hand and tell me what planet they think it is? What are you thinking, Matt?
Mars?
That's a good guess, because that is looking back towards the sun. Another guess?
Earth?
Earth, there we go. So all 6 billion of us are on that tiny, tiny little dot there. Hope you were smiling when we took the picture. And isn't that a beautiful shot? This was the cover of National Geographic magazine. So as much as I love Mars, Cassini has paid my bills for 15 years. I've been on this mission. We launched in '97, got to Saturn in 2004. We've been orbiting Saturn ever since. So back to the question, did I work on multiple things? Yes, I did, and it was really challenging because Mars demanded a lot of time and energy, and we were really stressed. Is it going to work? You know, and it's by JPL NASA standards, it was instant payoff. You go from launch to landing in a mere 8.5 months. It took 7 years to get to Saturn, but of course Saturn wouldn't wait. Cassini wouldn't wait. So I was trying to juggle those two projects at once, and that was really tough. And in fact, a lot of times I was on second shift for these Mars mission, we're in Mars mission control before landing, with the maneuvers, things like that, getting ready for landing. So I'd work second shift Mars, but I still had first shift work to do on Cassini. So it was a little bit tiring and exhausting, but of course I wouldn't trade it for the world, given these successes. And Cassini was very supportive of my little part-time summer job on Mars, but they're happy to have me back, so I can focus all my attention on Saturn again. But yeah, that's a great question, and what a challenge to try to juggle those two spacecraft, keep them flying, and keep both projects happy.
Great, next question's coming.
I wouldn't have it any other way. It was great.
Alexander Kelsey?
Did you use the same propulsion techniques for the Spirit and the Opportunity as you did with the Curiosity?
Same propulsion techniques?
Oh, great question, and thanks for the propulsion question too. It's softball, perfect for me. We generally did for cruise for sure. The cruise stage getting from Earth to Mars was exactly the same. We have these little tiny hydrazine thrusters, monopropellant thrusters, and those fire to keep the mission on course from Earth to Mars, those TCMs, trajectory correction maneuvers. So that was one good thing to keep the mission costs a little lower and to make it easier. Now, once we hit the atmosphere, things were very different because the last rovers used airbags, so they had no propulsion on the cruise stage. Whereas the Mars Science Lab had lots of propulsion. We had, if we can pull that one up, this is a still from the 7 Minutes of Terror. And what we'll see here, that's the heat shield, but see those plumes coming out the back of the heat shield? There were reaction control thrusters, RCS thrusters, that were firing to actually fly this. We weren't just a passive heat shield entry, we were actually flying back and forth doing bank turns like the shuttle does to shed speed and to really precisely control our landing. So that was the first bit of propulsion in the atmosphere on the descent stage. Then we had the descent stage itself had 8 big thrusters, hydrazine thrusters. There we go. See those firing? And that led even, not only, that slowed us down enough we could think about landing, but even then you didn't want to land on those rockets, so that's where the sky crane comes in, where we lower the rover on cables, but see the rockets up there still firing. So, yeah, that was and we built that propulsion system in-house at JPL. So that's a great source of pride among JPL propulsion people, is we built this thing and never got to test it till we tested the rockets, but you didn't get to test the system altogether until we're actually on the red planet. That was very nerve-wracking, but it worked beautifully. And then lowered the sky crane, lowered the rover to the surface, cut the cables, then that descent stage tilted 45 degrees, went off and crashed, Martian space junk, as it were, but it did its job. It slowed us down and got the rover safely to the surface. So lots of new propulsion challenges, all within that 7 minutes of terror. So, 10 years for that 7-minute moment. It's an amazing set of drama there.
And we weren't able to test everything all together, but it was so successful that we're actually making plans now to...
That's right. In the old days, NASA budgets in like the mid-70s were bigger, and in Viking, we tested the whole Viking rocket landing system. That was the first landing on Mars, 1976. We tested that in vacuum chambers, and we had pretty good confidence it was going to work. These days, the budgets are smaller. We don't have the money to be able to test the whole thing as a system, so that's very nerve-wracking. You do your best, you test it in pieces, and then you hope everything plays nicely together once you're on the red planet. Thankfully it did. But NASA was sufficiently impressed with this technique, they have assigned a mission to JPL, a new rover that's going to be similar to this one with the same entry, descent, and landing technique, the sky crane and all that, and that rover will launch in 2020. And I hope to get to work to that. Cassini will be done by then. I think we wrap up in 2017. So that might be just in time to start working another Mars rover. And so I'll be in my early 50s then, still trying to figure out what I want to be when I grow up. That's not a bad life to be living there, Lyle. So very lucky guy. And then we're not sure how this will scale up. We know airbags don't scale up that well. That's why we had to use the sky crane. But they're already talking maybe something like this could be used for a human mission to Mars. But we're talking another factor of 100, like 100 metric tons on the surface rather than 1 metric ton. So it's hard to think of a sky crane and how you're going to lower humans in one of these things, but they're thinking about it because it works so well for MSL. So we'll see what happens on that.
Oh,
great question. Thank you.
Ms. Soresi, did you have a question?
Does the weight and mass of the cargo change the amount of fuel needed?
Could you say that one more time really loud since you're way in the back?
Does the weight or mass of the cargo change the amount of fuel required?
Does the weight or mass? Yes, it does. This was a very heavy rover. The last rover only weighed maybe 200 pounds. This is 10 times more. So that we had to use a heavier launch vehicle. The Delta II was the NASA workhorse of the old days, cheaper launch vehicle. Worked great, has a very high success rate, but it just wouldn't get the job done. So we had to go to an Atlas V. I think we've got a video of launch. Maybe we can show that a little bit here. This is our Saturday morning after Thanksgiving, 26th of November, 2011.
T-minus 10, 9,
Stay with the countdown,
8,
if you will, because
7,
I'm superstitious.
6,
I don't think it'll work.
5, 4, 3, 2, 1.
Birdie,
Main
here he
engine
comes.
start,
You're going to get fried.
0,
Okay,
and
there he goes. Be
liftoff
careful.
of the Atlas V with Curiosity, seeking clues to the planetary puzzle about life on Mars.
So that's an Atlas V rocket launch. And so it's 10 a.m. East Coast time, 7 a.m. here. And I was working 12-hour shifts around launch, and mine started at 10 a.m. Well, let's see, no, it was midnight or noon to midnight. I'm a night owl. I love that shift, so I could sleep in every morning. But I didn't sleep in this morning. I came into JPL to watch the launch, wondering if I'd have a job. And beautiful shot here of the Atlas V rocket. So, this is a bigger rocket, more capability than the Delta II. And we needed that because this rover is 10 times heavier than the last two rovers. See, there go the solid rocket motors. We drop those off up in the Atlantic and recover them and reuse them. Cycling there. And I think this video goes clear to spacecraft separation.
Yep, it does.
And that was the fairing, the nose cone separation and jettison.
CFLR jettison. Right as expected, throttling up on the RD-180, everything looked good.
See the rocket firing? There's the
Spacecraft separation.
So that's the last human eyes have seen of the spacecraft. We push it off with springs, and the solar panels there carry the cruise stage to Mars. So all that happens within about 45 minutes after launch. That was a great, great day. Next to landing day, that was probably the best day on the project, just seeing us on the way to Mars, and knew we had a success there. That's a good question. Thank you.
Andrea Perkins, question?
How do you make the rover deploy instruments?
Once again, could you say that nice and loud? We caught the first part. How do you make the rover, and then we don't know what was after that. A little bit louder, please.
How do you make the rover deploy instruments?
How do we make, sorry, one more time, almost like you're shouting it.
Yeah, it's deploy. How do you make the rover deploy the instruments once it's there?
Oh, okay, the science instruments, once it's on the surface?
Yeah.
Yes.
Okay, that's a good question. We basically, as our NASA administrator says, or as the head of the MSL said here, once we've landed, we have a priceless national resource on the surface of Mars. So the scientists are like kids in a sandbox in a toy store. They want to go do everything and go crazy, but we don't want to do that. The engineers are cautious. They want to check everything out really carefully, incrementally. So we started looking at basic functionality, doing little short drives, then longer drives. We did our first sampling. We put it in the ovens. We did the first test of the laser. As we like to tell the Martians, we are armed this time. We have a death ray on board. That's what I call it. The scientists don't call it that. But we have an infrared laser that can vaporize rock from 30 feet away. And that way, even if we can't get to a rock, we can tell what it's made of. We look at the vapor cloud coming off the rock. And I think in my slides, I've got a picture of it being used on Mars.
Oh, okay.
Do you know which one I'm talking about?
Let me check. I've got this one right here. It shows a close-up.
I think in my shots, let's see. I think there's a feline nearby.
Oh, I know it.
Okay, so as we're pulling that up, and I asked the instrument people, I said, because this is what the students want to know, would that laser hurt you if you were, it's back before that, has its own slide. I said, would the laser hurt you if you got your skin in the way of the laser? And they're like, well, what do you think, genius? It can vaporize rock. So absolutely, it would burn your skin. And I think it's going to, let's see here. Keep going. Yeah, we'll find this here. Okay, so here's a picture of this being used on Mars. Let's see if I can get it. Now, of course, that's not true. No kitties were harmed on Mars or Earth. You know, dog people really like this cartoon. Cat people not as much, but anyway, that's our Martian death ray laser. So to answer your question, to get serious again, we check everything out very incrementally. We've done everything. All the science instruments are working, except the one thing we haven't done yet is drill into a rock and then process that sample. We're at a very scientifically interesting area right now. We're going to do that very soon, and then we will declare the rover is 100% completely functional. I can kind of show our landing area here. This is pretty cool. This is that the crime scene? Yeah, I love this shot. This is a beautiful shot because this is kind of the proof we didn't fake it all. Of course, you could say we faked this too, but we have good orbiters around Mars that have great cameras, can see 1-foot resolution detail. So this is kind of the proof that that we landed, and there's some things on the surface that weren't there before. So we see Curiosity, there's blast marks from the rockets, kind of in the center of the image. We have where the heat shield dropped off in the lower right. We can see the heat shield crash site there. Lower left, we see the back shell and the parachute. See the white of the parachute there? That's where it landed. And then where it says Sky Crane up there, well, that's not really the Sky Crane anymore. That's the Sky Crane crash site. So the thing that lowered the rover down went off and crashed in a big heap and left debris field there. So, one thing the scientists love where we landed from Curiosity, if you head to the right about 500 meters or 500 yards, 5 football fields, there's kind of 3 different terrains that meet there in one point. And we call that Glen Elg. And scientists love that because you drive to that one point and you can sample 3 different types of terrain all basically at the same time, within days of each other. And so that's what we've done. We've driven over there, and on the way we discovered rounded pebbles that seem to have formed a Martian brook. So we're the strongest evidence ever of liquid water. Here are those pebbles. Kind of looks like a concrete sidewalk dug up. And those rounded pebbles are too big for the wind to have transported. So we know water flowed on Mars. A few feet per second, probably ankle deep to waist deep. So that's very exciting. Definitely the strongest evidence of Mars is water yet. Not there today. It's dry and cold desert, but you know, did life start there back when the water was there? So to answer your questions, we test things out very cautiously, systematically, sequentially, and we're almost there with a full checkout. All the science instruments are working great. We're going to get that last drill sample, make sure that works, finish up where we are, and then start heading for those hills, the Mount Sharp and all those interesting geological layers. So we can't wait to get there to see what the Martian rocks have to tell us, using all our science instruments.
Okay, Mike.
Great question, thank you.
And nice and loud, Mike.
What type of metal is the Mars rover made out of?
It's a good question. We use aluminum a lot. We use titanium. Those are both strong and lightweight. Not a lot of steel or iron because it's heavy, and we don't think it would rust on Mars. Mars has very little water. It's not a rust issue. It's a weight issue, weight and strength. We also use what's called composite materials, which are it's an epoxy type thing, but with fibers inside. So aircraft are more and more being made of this. It has the strength of steel, but it's much more lightweight. And so there's a lot of that on the rover. We use kind of hollowed out structures, honeycomb structures to keep things light also. The weight is always a premium when you got to launch something and land it on Mars. But that's a great question.
Lindsay.
But maybe that's a future material scientist in the room.
Oh, maybe. We'll see. Lindsay, you had a question?
When the rover is descending into Mars' atmosphere, what's the top speed and what was the maximum time?
Okay, that's a great question. Top speed was basically right as we hit the top of the Martian atmosphere because, as I mentioned, it's going like 8,000 miles an hour as it approaches it, but Mars gravity actually accelerates us and sucks us in, makes us go even faster, which stinks because then you got to slow down to zero more. You know, you got to go from 13,000 to zero instead of 8,000 to zero. And so the answer is about 13,000 miles an hour. And the peak temperature, that was in the 7 minutes of tear, I think it was like 1,600 degrees in front of the heat shield, which is really, and they didn't say in there what
it's
the units.
1,600 Fahrenheit.
Fahrenheit.
Excuse me, Celsius.
Celsius, okay,
Yeah,
so
Here we go.
over 2,000 Fahrenheit there. Do we have that somewhere?
Yeah, here we go.
Oh, great. Wow, 3,800 Fahrenheit. So what's the surface of the sun?
Anywhere from about 5 to 10.
5 to 10. So we're approaching kind of the level of the surface of the sun. And that's also, 3,800 is, there's nothing that won't melt if you keep it at 3,800 for very long. So we have this carbon phenolic heat shield, and it actually vaporizes half of the mass of the heat shield on purpose. But that's good because you build the heat shield thick. There's a shot of the heat shield right there. And as you come in, it melts and carries the heat energy away behind you as it melts off. But if you make it thick enough, it's okay. You can still protect the instruments inside, keep them nice and cool, basically near room temperature. So that's the challenge, is it's because the heat of friction, even in Mars' thin atmosphere, is really high, 3,800 Fahrenheit. Wow, I'll remember that for the next time. And that's a great question. Thank you.
Kaylee Kavanaugh?
About how many pictures does the rover take in a day?
Oh, that's a good question. I'm not sure. I know I think we've done tens of thousands probably since landing.
Right.
And we've been on the planet for about 5 months, so let's call it 150. It's probably on the order of 50 a day, somewhere in that kind of range. It's probably like much more than 10, probably less than 100. Yes, so, some, obviously it's doing a lot more than just taking pictures. We have all of this, these sample science and weather measurements and all this. All those instruments compete with each other for the limited bandwidth to send the data back to Mars. But we're humans, we see in the visible. Obviously, we want to see what the rover has to see too. Here's a good example. The team deserved a well-needed break over Christmas holidays. So we landed on, we set up in a little place. We called it Grandma's house because we all went to Grandma's house for Christmas. So including the rover, just checked out some rocks. And since it was parked for a couple weeks and we took a nice break, of course the rover doesn't rest. We don't let the rover rest, and as tired as it might be. We made it do a 360-degree panoramic view from where it's at high resolution. So it took a lot of images there while we were all enjoying our holiday dinners. And it was able to do that because it wasn't moving and doing other science. It was stuck in one, not stuck, but we parked it in one place, and that way it could get the high resolution. So it probably took a lot more pictures during that window than during an average day, let's say.
I know that Spirit and Opportunity took something like 100 or 200,000 pictures so far.
Wow.
But Curiosity has 17 different cameras, so quite a few more possibilities for pictures as
That's
well.
true. Now, of course, Spirit and Opportunity have been doing it for years, but as Lyle said, you know, we got 17 cameras on board, so there's all kinds. There's the stereo cameras. If you get a pair of 3D cheap glasses, Google 3D Mars on the internet. You can sit at your computer with your 50-cent pair of glasses and feel like you're on Mars. Because not only from this rover, but the last rovers and from our orbiters too, they all have stereo imaging capability. So your generation will probably get to go to Mars, and boy, am I jealous. But especially for me, if I want to feel like I'm on Mars, that's what I have to do. Google 3D Mars, get my glasses on. But then you really feel like you're on the red planet. That's a cool thing to do. So I encourage you all to check that out too. Next question.
Yeah, Griffin, go ahead.
Why nuclear, and how do you put a nuclear power plant on a rover?
Okay, that's a good question. We've had Mars rovers before, as I mentioned. Pathfinder was a little microwave oven-sized rover. It had a top-mounted solar panel, and that's great because Mars does get some sun. It's less than the Earth, the inverse square law, which you'll learn about soon. And the Mars atmosphere is thin. That's good, so you lose less sunlight that way. The problem is Martian dust. It's this real fine iron oxide rust, dust that floats everywhere, and that tends to fall out on the solar panels, and it can cut your solar power by up to 1% a day. So if that's happening for years, you're not going to have a mission. You're going to lose all your solar panel, your solar power. And the Spirit and Opportunity fight dust too. We thought that would limit the mission surely. And then there's Martian dust devils. Oh, that's even worse. They kicks Martian dust up. We thought that'll kill the mission for sure. Well, the Martian dust devils came along towards Spirit and Opportunity. We thought this is the end. Then we looked at our pictures. The dust devils clear the dust off the solar panels. So now we hope and pray for dust devils every day. And they've done pretty well coming to help Spirit and Opportunity out over the years. Despite that, Mars dust is still a huge problem. And we didn't want to count on that. That was a backup plan for the Mars Science Lab. But since the instruments are on top and there's ovens and that all was the area where you need solar panels, plus we wanted something that could get through the dust and maybe work at night. Solar panels don't work at night. You can charge a battery, but you basically have enough time, hard enough time to stay warm at night. 100, 200 below at night, that's very difficult. So someone said, let's put an RTG on board, radioisotope thermoelectric generator. And here it is in the back with the radiative fins. It's not a nuclear reactor. It's plutonium inside is hot, radioactively hot, and alpha decay converts, I don't know what it goes to. I don't know what plutonium decays into. But it's not a reactor. We don't fire neutrons at it and have a nuclear reaction. It's just this natural radioactivity of plutonium makes it hot. And then we use the heat in a thermionic converter to get electricity to the rover. We love these. They're expensive, but they have no moving parts. They work for decades. The half-life of plutonium is 76 years. So this is like a reliable nuclear battery with no moving parts that lasts for decades. But it's very low power. The whole rover has 110 watts of power. So the rover, that huge battery there, could only power 100-watt light bulb. And if anybody who used a blow dryer this morning on their hair? Anybody? Okay, what's your wattage on your hair dryer? Anyone know their wattage on their hair dryer?
1,500.
There you go, 1,500 watts. That's a pretty good size. So you need 15 of those nuclear batteries just to run your hair dryer, right? But the whole rover, the driving all science sensor, works on about 110 watts of power. Unbelievable. So we love those nuclear batteries. They're controversial. They've got plutonium on board. People are worried about a launch accident because plutonium can be dangerous. So we had fun just proving that even if you had a launch accident, you cannot spill the plutonium out. And we have these nuclear batteries on Cassini and Galileo as well, Jupiter orbiter and Saturn orbiter. And so we had a lot of fun. We set them on fire and blew them up and shot guns at them and all kinds of stuff. And we just could not get the plutonium out. So that's how we proved you could still launch. We can't say there won't be a launch accident. We know that launch accidents happen. We had to prove that the nice people of Florida couldn't be hurt, even if there was a launch accident. So that's how we handled the plutonium issue. But we love them. They're expensive. You know, they've got some issues, but for a reliable power source with no moving parts, we absolutely adore it. And we would have loved to have had on Spirit and Opportunity too, but the timing was right for Curiosity. And expect those on future rovers, and I would not be surprised to see those on human missions. Although you got to be a little careful because they are radioactive, so you'd have to shield the spacecraft, protect the humans from those radioactive nuclear batteries.
Because when they were building it here at JPL, they actually didn't have the plutonium in it.
That's
the
right.
Plutonium was put in later.
Yeah, we had a mock-up here that's something that looked like it and the right mass and had some heat, but you got to put on the radiation suits when you load those things on the spacecraft down in Florida, which we did. But we love those RTGs. They work great, and that's a great question. And there's a public misconception. They think there's a nuclear reactor on board and people could get hurt from it and all this. It's not a reactor. It's a nuclear battery. But they work great, and we hope to use them in the future, I would say.
Great.
That's a great question. Thank you.
Do you have time for one or two more, do you think?
Yeah, we
Sure.
have about 5 minutes or so.
Sure.
Okay, good. We'll take Patrick Corbett next.
My question was already.
Oh, your question was answered already. Well, that foils my plan, doesn't it? Katie Lewis?
Okay, does the planet Mars have any seasons, or did it ever once have seasons?
Does the planet have seasons?
Seasons. Oh, great. I missed the word seasons. That's the clear. Yes, it does. That's a great question. Mars is tilted about 25 degrees on its axis. Earth is tilted about 23. So it actually not only has seasons, they're very similar to the Earth's seasons, but the Martian year is twice as long, so the seasons are twice as long. So when I talk to elementary schools, I say, hey, you guys would get 6 months of a summer break on your school year, but then you'd have 6 months of autumn, 6 months of winter, and 6 months of spring. You'd have an 18-month school year. And that's when they decide they don't want to head to Mars, even for that nice 6-month summer break. So the season, now Mars, Earth's tilt, the 23.5 degrees, is stable over a long, long time because of our moon. And that's kept the Earth's climate fairly stable. Mars is not. Mars has these little tiny moons, very little gravity, so the Mars tilt varies from 0 degrees to like 60 degrees over just a few million or billion years. And that's a problem. That's why sometimes the equator can be like the poles and the poles can be like the equator. That's why there's water ice beneath the surface near the equator. So, and it's also, they speculate that that's one reason why Earth was able to get life going here is because we have this stable tilt and a stable climate. If life got going on Mars, it might have been tough for it to maintain if the tilt of the axis is getting so severe. Because if you have a 60-degree tilt, the seasons are going to be the same length, but really severe on Mars. Whereas if you go to 0 tilt, there's no seasons at all on Mars. It's always the same no matter where you're at. So, I mean, you get more sun at the equator still, but there's no change in seasons like there is on Earth due to the Earth's tilt. That's a great question. Thank you.
All right, Levi.
Is it complicated and or confusing from sending the program to the rover because of the time difference?
And when you say time difference, you mean the fact that it takes the time for the signal to get to Mars?
Yeah.
Yeah, that's a great question. And I forgot to mention that earlier, so thank you for bringing that up. We would love to drive these rovers like a video game. That would be awesome because we could get a lot of science done. Albert Einstein, the pesky guy, does not let us have that luxury. And that's because the distance between Earth and Mars varies a lot in its orbit, and we see that here. At their closest, they're still millions of miles apart. At their furthest, they're hundreds of millions of miles apart. So the signal coming from Earth to Mars takes about 4 minutes to get there, best case, and about 20 minutes to get there, worst case, depending on where the planets are. So imagine a video game where you jiggle your joystick, and you've got to wait 8 minutes to 40 minutes. It's round trip, right? You have to get the signal, get to Mars, then you have to see what happened, when you drove the Rover. So people aren't going to play that video game very long because of that, and that's called the one-way light time or two-way light time. And that's why we cannot drive these Rovers like a video game. That's the bad news. The good news is we program smarts into the Rovers so that they can drive themselves. We can say, there's a rock here, you're here, you figure out how to get from here to there without driving over a cliff or stalling or driving up a rock that's so steep you're going to get stuck. Or if it slips in the sand, it's smart enough to know that so it doesn't bog itself down and dig its wheels in. We've learned a lot of those lessons from the last Rover, but it is a pain. You know, if you guys and gals figure out a way to circumvent the speed of light so we can get a signal there faster, please let us know. After you get your Nobel Prize in physics, we'll talk, and we can definitely use that to drive our Rovers a little more quickly.
I mean, it's safe to say that you have really had thousands of people working on these projects as you look at them. Any pieces of advice that you would give to these kids if they're interested in working on projects like these? What skills do they need to have?
Absolutely. And I'll start by saying, not just for this kind of career, my advice to kids, and your parents may hate me for this, but if you're passionate about music, drama, whatever it is, even if you don't think you can pay the bills, you know, it's good to have a backup plan, but what I did is I followed my passions. And that led me here, and that's why I have a job that doesn't feel like work. And I get to come to work every day. And not everybody wants to do this career. That's fine. I understand that. Follow your passions, and it will lead you to the right job. Now, I hope maybe to see how cool this stuff is and what we get to do for a living might spark some more interest for people to think this might be a fun career. And of course, if you do want to head to that direction, the things to do: work really hard in school, obviously. Math and science, take as hard a classes and as many of those classes as you can. Work really hard in them. Plan to go to at least a 4-year university and major in a STEM discipline: science, technology, engineering, or mathematics discipline. And we have every kind of STEM discipline here at JPL. Engineers, mathematicians, biologists, chemists, physicists, fluids engineers, thermal, probably everybody civil engineers.
You can almost take those and combine them. You know, you've got astronomers and you've got biologists. We've also got astrobiologists. So
any of those technical careers, there's a place for you here at JPL or in the broader scheme of NASA. So maybe I'll close with this. I'll tell you the kind of questions that interested me growing up and that interest me now. And these are the questions I get to help answer every day. And I'm a very tiny part of the big JPL NASA machine that gets to help answer these questions. But literally, every day when I go home, I feel like I've tried to help answer these little questions. And these are the tiny little questions that I'm working on, that we're working on here. How did life start? How old is the universe? How did we get here? Are we screwing up the planet so our kids and grandkids can't live here? Is there other intelligent life in the universe? What's the fate of the universe? Will it expand forever or collapse down in a big crunch? How did the planets and stars form? Will we make contact with other civilizations? What's our future in this solar system and beyond? So if these questions interest you, this might be the right place for you young men and women to come work one day. So keep working hard, math and science. Thank you for your time today. And any last comments, Lyle?
No, I just want to thank you all for taking time to have us in today, and I want to thank Todd for taking time out of his busy schedule. I know he's got a lot of work that he's doing, so I appreciate it. Thank you very much.
You're welcome, Lyle. It was a pleasure all mine. It's wonderful to talk to all of you, and have a great day up in New York. Happy New Year, everyone, and hope to see you here maybe in about 10 or 15 years. Keep working hard in math and science.
All right, thank you very much. Goodbye. You guys can wave goodbye. Hey. All right, ladies.